Hello, I'm Kang, and I'm a master student at KAIST in South Korea. Let me present our work, personalized graph summarization, formulation, scalable algorithms, and applications. This is a joint work with Kyuhan and Kijung. A graph is a data structure widely used for representing relationships between objects. It naturally represents relationships in various domains such as social network, purchase history, and web graphs. As the World Wide Web and storage techniques become advanced, the size of graph data is growing rapidly. For example, the number of users in Amazon.com increased 7 times in the past decade. In other words, the number of nodes in the graph representing purchase history has increased. Then, how do we efficiently utilize such large graphs? Graph summarization is a promising graph compression technique, and there are two types of graph summarization depending on the loss of information. In this work, we focus on the lossy version of graph summarization. As in the below figure, given an input graph, graph summarization compresses the graph into a summary graph. Since the summary graph is also in the form of a graph, we can directly process queries on the summary graph, and we also can apply other graph compression techniques to the summary graph for further compression. Given an input graph, graph summarization aims to find the summary graph. In the below figure, given an input graph G with 5 nodes and edges, we compress the graph into a summary graph G bar, where each node is a group of nodes in the input graph. Note that the summary graph has only 3 nodes and 2 edges. Formally, what should be the objective and the constraint? The objective is to minimize the difference between the input graph and the graph restored from the summary graph. For example, we can aim to minimize Manhattan distance between their adjacency matrices. Please refer to the paper for the detailed restoration process. And the constraint is that the size of the summary graph should be within a given budget. For example, we can measure the size of the summary graph using the number of bits required to encode it. However, there is an inherent limitation in graph summarization. The limitation is that the amount of information lost becomes larger inevitably as we compress the input graph more. Then, how can we mitigate this inherent limitation? To this end, we notice the fact that people often have different levels of interest in different parts of a given graph. Consider a large social network. The network includes people in KAIST where I work at and also people in a land far away. If I have to bear information loss to compress the social network into a summary graph, which information should I prioritize to preserve between connections between people in KAIST and connections between people in a land far away? Sure, intuitively, I prefer to better preserve the connections between people close to me which are more likely to be useful to me. In other words, in order to obtain a compact representation of a given graph, it is better for me to suffer the loss of information about the land far away. This is an example of a well-known phenomenon called the first law of geography. According to the first law of geography, everything is related to everything else, but near things are more related than distant things. As another example, in a citation network, we are more interested in citations in our field of study more than citations in other fields. Moreover, in a road network, we prioritize information about places closer to us more. Based on these motivations, we formulate a new problem, namely personalized graph summarization. Personalized graph summarization aims to produce a summary graph personalized to the target node. To this end, it requires the set of target nodes as an additional input, and it aims to minimize the reconstruction error personalized to target node T. The symbols V and E denote the set of nodes and edges, and the symbols S and P denote the sets of supernodes and super edges. As explained, a supernode is a subset of V, and a superedge is a pair of supernodes. We maintain the size of a personalized graph, that is the number of bits to encode the output within the budget. Let me describe how the personalized error, which is our objective, is defined. The personalized error is defined as the weighted sum of the reconstruction errors. The symbol W denotes the personalized weight on each node pair I and J, and the symbols A denotes the adjacency matrix of a graph. That is, the adjacency matrix of the input graph and that of the restored graph are being compared. In this figure, we can see that the edge between nodes A and D is restored incorrectly. The personalized weight of a pair of nodes depends on their distance from target nodes, and I provide its definition here. Given a node I and the target node set T, the symbol D is the minimum of the number of hops between nodes in the target node set and node I. In this figure, I compare the personalized weight of three node pairs in the given graph. The personalized weight on the node pair closer to the target node set is larger. Let me describe our optimization algorithm Pegasus for the personalized graph summarization problem. Pegasus is effective in personalization useful for application and scalable to large graphs. These properties will be shown one by one in later slides. Note that Pegasus is largely based on the state-of-the-art algorithm for the non-personalized graph summarization. The inputs are an input graph, a size budget set of target nodes, and the maximum number of iterations. The output of Pegasus is a summary graph personalized to the target node set. Here I'll outline the procedure. We first initialize the summary graph, then we repeat the dividing and merging step Tmax times. During iterations, if the size of the summary graph becomes smaller than the size budget, we terminate the iterations. Finally, if the size of the summary graph is larger than the size budget, we specify the summary graph. Let me describe each step in detail. In the initializing step, we initialize the superedges and supernodes of the summary graph as shown in the figure, and we set a threshold to 0.5. Note that each supernode in this figure contains exactly one node. Next, in the dividing step, we divide the supernodes of the summary graph into groups U. By exploiting min-hashing, we get groups of the supernodes with similar connectivity. In this figure, we represent the same group with the same color. In the merging step, we merge supernodes to reduce the size of the summary graph. In each group of groups U, we repeatedly merge pairs of supernodes in a group if the saving due to the merger is larger than the threshold. Here, the saving is roughly the saving in both personalized error and size. If we merge two supernodes, we'll selectively add super edges instead to the merged supernode based again on the saving. In the figure, the supernode F is merged with G and only the self-proof is added. As explained in the outline, after the dividing and merging step, if the termination conditions are not met, we will repeat the dividing and merging step. In this dividing step, we divide supernodes into groups one more time. It should be noticed that min-hashing, which is a randomized algorithm, gives different partitions in each iteration. As before, in the merging step, we merge supernodes to reduce the size of the summary graph. In this figure, the supernode D union E is merged with C, and the super edge incident to the union B is added. After repeating the dividing and merging steps at most Tmax times, if the size of the summary graph is still larger than the size of the K, we further drop at super edges to maximize the saving. In this figure, we can see that a self-proof is dropped. Recall that in the merging step, each pair of supernodes are merged only if the amount of the saving is larger than a threshold zeta. It is known that controlling the threshold is important for obtaining high-quality summary graphs. Specifically, using a small threshold may merge supernodes myopically when better pairs with larger savings can be found later. On the other hand, using a large threshold may make supernodes remain without being merged even when their merger leads to a saving. Previous algorithms decrease the threshold over iterations, and to this end, they use a fixed rule independently of input graphs. However, we control the threshold adaptively based on the savings in the previous iterations. Specifically, we collect the savings at unsuccessful searches where the saving does not exceed the threshold. Then we use the top 10% entry of the collection as the threshold at the next iteration. This way of updating the threshold decreases the threshold adaptively based on the distribution of savings at each iteration. Let me move on to an application of the Pegasus to distributed multi-query processing. Real-world graphs such as online social network web graphs and purchase histories are often too large to be stored in a single machine. Thus, they are typically distributed across multiple machines. How a graph query is answered on such distributed graphs. Example queries include k-nearest neighbor queries and neighborhood queries. Given a query in typical system, multiple workers cooperate to answer it, and to this end, they communicate with each other. At this time, there exists inevitable communication overhead, and we waste our resource on them. Then, how can we eliminate this communication overhead? To eliminate the overhead, we create multiple summary graphs with different sets of target nodes. Each summary graph fits in main memory of a single worker, and different summary graphs are loaded at different workers. Each query is answered by a worker with a proper summary graph without communications. Let me describe how queries are answered in a communication-free way step by step. Given a large graph, we first partition the node set into subsets. To this end, we use the Roubaix method while any graph partitioning method can be used instead. In this example, we suppose that nodes are portioned into three subsets V1, V2, and V3, and there are users U, V, and W in each subset. First, we produce a summary graph personalized to the V1 and route it to the worker 1. As we produce a summary graph personalized to V2 and route it to the worker 2. Finally, we do the same process on V3. As a result, we have three summary graphs with different focuses, and they are loaded on three workers separately. How can you answer queries using the summary graph? Each query is answered a single worker without communications. For example, queries about node U are answered to the worker with the summary graph personalized to the subset with U. Similarly, queries about node W are answered by the worker with the summary graph personalized to the subset with W. Summary graphs used to preserve relatively abundant information about queried nodes. Thus, answers are approximate but can be accurate. Also, note that multi-queries can be answered in parallel as workers perform independently. Let me share our experimental results. We designed experiments to demonstrate that our model Pegasus is effective in personalization, useful for applications, and scalable to large graphs. In our experiments, we used 6 real-world graphs from various pairs and synthetic graphs with up to 1 billion edges for a scalability test. We compared our method with the state-of-the-art graph summarization method. When showing the usefulness of our method for distributed multi-query processing, we compared it with the graph partitioning method. Here are some experimental details. We considered the three types of node-simulated queries for evaluating the quality of summary graphs. We measured the accuracy of approximate answers from the summary graph by comparing them with the ground truth answers using two measures. They are symmetric mean absolute percentage error, which is SMAP in short, and Spearman correlation coefficient. Lastly, target nodes are sampled uniformly at random. In order to show the effectiveness of Pegasus in personalization, we measure how the size of target set affects the personalized error. As Pegasus focuses on a smaller target set, the personalized error decreases, and in other words, the information close to target node set is well preserved. Based on these results, we can say that Pegasus successfully provides personalized summary graphs. For effectiveness, we additionally consider three types of queries on target nodes, and we measure the accuracy of the answers from summary graphs obtained by different algorithms. The answers from personalized summary graphs were up to 3.86 times more accurate than those obtained from non-personalized summary graphs of the same size in our considered datasets. Here, the plots have the size of summary graphs on the x-axis and the accuracy of query answers on the y-axis. Note that Pegasus provides a significantly better trade-off than the state-of-the-art non-personalized graph summarization algorithm. These results support the effectiveness of Pegasus in personalization. In order to show the usefulness of Pegasus for distributed multi-query answering, we obtain 8 summary graphs personalized to 8 communities in each graph. Then we answered each query using the summary graph personalized to the community that contains the query node as explained earlier. The answers from the personalized summary graphs are compared with the answers from baseline approaches. As baseline approaches, we used answers from a partition that each query node belongs to and the answers from a non-personalized summary graph. The answers from the personalized summary graphs are most accurate under the same storage budget, regardless of types of queries in all considered datasets. We have just shown that Pegasus is useful for distributed multi-query processing. We also tested the scalability of Pegasus and it scaled linearly with the number of edges, which is also supported by our theoretical analysis. Noticeably, Pegasus successfully summarized a graph with 1 billion edges. And this result confirms the last property of Pegasus. Let me conclude my presentation. In this work, we introduced a novel problem which we call personalized graph summarization. We mathematically formulated the problem based on the first law of geography, and we proposed an optimization algorithm Pegasus. We showed theoretically and experimentally that Pegasus is effective in personalization, useful for applications, and scalable to large graphs. Here are the references. Thanks for listening.